Hello guys, I'm Genevieve Edwards and I am doing biogeochemical cycles for rivers and streams. Rivers play a significant role in the transportation of carbon, nitrogen, and other mineral nutrients from upstream to downstream regions. And these substances also influence the geochemical processes operating in water. Chemical and physical factors such as temperature, light, riverbed substrates, and dissolved substances in the water are the main factors that influence biogeochemical processes occurring in the water. This figure shows important biogeochemical processes that occur in river water during downstream transport. These processes include production, respiration, decomposition, nitrification, denitrification, and others carried out by micro and macroorganisms. So first, I'm going to talk about nitrogen in rivers and streams. So where does nitrogen come from in rivers and streams? First, you have biological fixation, which is by bacteria and cyanobacteria. Latent fixation, which is reduction of gaseous nitrogen in the atmosphere, which is N2. And then you have runoff from human fixation from crop production and energy production. You have forms, sources, and loss of nitrogen in water. Some forms would be dissolved nitrogen, ammonia, nitrate, nitrite, and organic nitrogen. Now, sources of nitrogen in the water would be precipitation, which is rain, fixation, surface and groundwater drainage. Now, losses of nitrogen would be effluent outflow, reduction with loss of gaseous nitrogen, and absorption into sediment. You have form. Now, this is just a visual that shows what I talked about in the last two nitrogen slides. The different sources and forms of nitrogen and how nitrogen actually gets put into our rivers and streams, and how it cycles within the stream itself. Next, I'm going to talk about phosphorus. Phosphorus is an essential nutrient for living processes and often the limited nutrients in an aquatic ecosystem. Phosphorus in aquatic systems is usually divided into solid and dissolved forms. Total phosphorus includes all phosphorus found in a water sample. Most of this phosphorus is found in a solid form. Phosphorus in rocks and other mineral forms is inorganic. Organic forms of phosphorus are incorporated into biological materials such as plants or animals, their dead remains, and waste products. The fraction of total phosphorus that can pass through a fine filter is called dissolved or soluble. Dissolved forms include organic and inorganic molecules. The form that is most readily taken up by aquatic plants is inorganic molecule called orthophosphate. Phosphorus is not highly soluble, fine and tightly the molecules in the soil, therefore mostly reaches waters by traveling with runoff soil particles. Phosphates also enter waterways through fertilizer runoff, sewage seepage, natural mineral deposits, and waste from other industrial processes. These phosphates tend to settle on river and stream beds. As sediments are stirred up, phosphates may re-enter the phosphorus cycle, but they are more commonly made available to aquatic organisms by being exposed through erosion. Water plants take up the waterborne phosphate, which then travels through successive stages in the aquatic food chain. Unlike the nitrogen cycle, the phosphorus cycle includes neither gaseous components nor oxidation state changes. Most of the transformation of phosphorus are from dissolved to particulate, or the reverse particulate to dissolved, or from inorganic to organic, or also the reverse organic to inorganic. Now, too much phosphorus in an aquatic ecosystem can be a bad thing. Phosphate stimulates the growth of plankton and plants, favoring weedy species over others, which causes an algal bloom. The excess growth of these plants tend to consume large amounts of dissolved oxygen, potentially suffocating fish and other marine animals, while also blocking the available sunlight to bottom-dwelling species. This is known as eutrophication. Now, this can happen also if there's an excess of nitrogen too. Next, I'm going to talk about carbon, mainly carbon dioxide, in rivers and streams. Carbon dioxide is found in water as a dissolved gas and is very soluble. Most carbon in rivers originate as atmospheric carbon dioxide and either cycles back to the atmosphere or settles in sediments of the coastal oceans where it is eventually buried. Aquatic plants depend on carbon dioxide for life and growth, but pollution can produce too much carbon dioxide. In these conditions, fish have a hard time getting the oxygen they need from water and can suffocate and die. Now, a healthy aquatic ecosystem depends on a good supply of oxygen being dissolved into the water column. Oxygen enters water through air or as plant byproduct. From the air, oxygen can slowly diffuse across the water surface from the surrounding atmosphere or be mixed in quickly through aeration, whether natural or man-made. The aeration of water can be caused by wind, riffles, waterfalls, groundwater discharge, or other forms of running water. Dissolved oxygen is also produced as a waste product of photosynthesis from phytoplankton, algae, and other aquatic plants. Factors that affect DO. Temperature. The solubility of oxygen decreases as temperature increases. Fertilizer runoff from farm fields and lawns can affect DO. Bacteria that breaks down this material, sort of like going to overdrive and use up the available oxygen in the water. Algal blooms can cause low DO also. As the algae die and decomposes, the process consumes a lot of the dissolved oxygen in the water. Factors that Now, to tie this all together, I'm going to talk a little bit about nutrient spiraling. Nutrient cycles describe changes in nutrient states through time and usually do not consider a spatial component, but water and streams have a very strong spatial component. Now, since these nutrient cycles occur simultaneously with downstream transport, nutrient transformations in streams are conceptualized to as nutrients spiraling throughout the stream. Now, this just means the state that a nutrient is in is also a function of its distance downstream. The spiraling length represents the distance over which the average nutrients atom travels as it completes one cycle of utilization from a dissolved available form, passes through one or more metabolic transformations, and is returned to dissolved available form once again. The spiraling length is usually shorter if the nutrient is retained longer in particulate form. The utilization of the nutrients is more intense. So if your ecosystem function has not been impaired, the stream retains nutrients longer and may even lose more nutrients to the atmosphere through diffusion. I hope this presentation was able to give you a detailed look into the complex biogeochemical processes in rivers and streams. Thank you.